Right, we've seen that these four inorganic ions, these water, the hexaqua complex ions, we've seen that they're all acidic. They all got some acidic properties, and the reason why is because the central metal ions, so in the case of copper, you have water molecules forming a dative bond to it. Well, the copper withdraws electrical charge out of the water molecule, so it makes these bonds a little bit weaker, and protons can be released. So they're all a little bit acidic. Now, if they're acids, that means they're going to react with bases, and we're going to see how they react with sodium hydroxide. So they all react in quite a similar way, but I'm going to use copper as an example. Okay, so if you add some sodium hydroxide to copper, hexaqua ions, so it's a copper sulfate, what will happen is you will remove 2 protons. Okay, so I've got 2 OH minus, and so that will give you, if you remove a proton from water, it turns it into an OH minus, so that's going to give you H2O 4 OH, 2 of them. And what's the charge on that? Well, it's going to be uncharged because you've got 2 negatives on the OH minuses, 2 positives on the copper. It's uncharged. Now, what that means is that it will precipitate out of solution. If you've got all of these loads of copper 2+ ions in solution, they're going to repel each other because they're all positively charged. Once you lose that overall charge, then these things have got loads of water molecules around them, datively covalently bonded to them, and so there's plenty of possibility for one copper complex to hydrogen bond. One of these will hydrogen bond to the one next door, and so you get these. They stick together, and it's a very gelatinous sort of precipitate, and that's because you've got a lot of water trapped in it, all held together with hydrogen bonds. And the same thing happens with all of them. Okay, obviously with the 3+ ones, like the iron 3, it's going to have to lose 3 protons. Okay, so 3+, and you're going to have 3 OH minuses, and then you will form H2O 3 OH 3. There's no charge on that, and you get a brown gelatinous precipitate. Same thing happens with iron 2, and the same thing with aluminium. Now you might think, well, why can't you remove any more OH minuses from that? Why doesn't that happen? No, it doesn't. So you think, oh, well, you can remove another H+ from that, and maybe form Fe H2O 2 OH 4. Now that would be negatively charged if you could form that, because there's 4 minuses on the OHs and only 3+ on the iron. But that doesn't happen. Once it's become neutral, then you don't remove any more H+s. That's true for all of them except for aluminium, which I'll come to in a minute. Okay, so let's see what would happen if you did this experiment. We'll do a little results table, what you would observe. Right, so we've got here's the hexaqua complex. In writing that's the same, you're writing down the full formula. So I just write Cu2+, and it's understood there's waters there. Fe2+, Fe3+, and aluminium 3+. So let's see what happens when you add NaOH solution. So dilute NaOH, 1 mole of solution or something like that, 1 mole per decimeter cubed. Right, if you add that to copper sulfate, you get a blue precipitate of copper H2O 4 OH twice, and nothing else happens. That's the end of the story. Okay. Iron 3 is very easy. Okay, what happens there is you're going to get a nasty, horrible brown colored precipitate. So you get a brown precipitate of iron H2O3 OH3, and nothing else happens. It's the end of the story. With the iron 2, it's a little bit more complicated, right? Iron 2, you get a green precipitate. It's a fairly dark green precipitate. And you can see the color of the precipitate tends to follow the color of the hexaqua complex. And that's going to have a formula Fe H2O 4 OH2. But then if you leave that, what happens is it oxidizes in the air. The oxygen reacts with it, and it oxidizes the Fe2 plus, that's the 2 oxidation state, up to the 3 oxidation state. So if you leave it, it oxidizes, and it will form it will go brown. Fe H2O 3 OH3. And when you do this very often, if you've got your test tube of precipitate here, let's draw it. I'll do it in black. So you've got there's your test tube, and you get this sort of green precipitate here. But you notice at the top, it starts going brown at the top first. Well, it turns brown at the top, of course, because you've got it's easier for the oxygen to get to it. So it oxidizes quite readily in air. Aluminium, that one is a bit more complicated, because first of all, if you add a little bit, you will get a white precipitate of aluminium H2O3 OH3, and if you leave it, sorry, if you add excess, it redissolves. And that's because aluminium, this one can you can remove another H plus, and it will become charged again. So it will become Al H2O2 OH4, and that will have a negative charge on it, and that is soluble. So if you add excess sodium hydroxide with aluminium, it will redissolve. Now, if you look in some textbooks, it says that the species that it forms is that. In others, it says that you replace all of those hydroxides and you're going to get AlOH6, and of course that would have a charge of 3 minus. It'd also be soluble. If you look in the mark schemes, they don't mind whichever one you write down. I always write down where it's just 4 OH minuses, but either answer is okay. Right, so let's just have a little think about this species here. Okay, and this species is said to be amphoteric. Now, amphoteric means, you probably know already, but it means it can react with acids and it can react with alkalis as well. And let's just see why that can happen. Okay, so rather than drawing an equation, a sort of conventional equation, I'm going to put down this Al H2O 3 OH in the middle. That's no charge. Now, if I add alkali, excess alkali, I can pull another proton off, and I can form Al H2O 2 OH4, and that's got a negative charge on it. If I add acid, well, you can make this reaction go backwards. You can turn it back into the hexaqua. You'd have to add 3 H pluses. You'd turn it back into that H2O6 3 plus. So this this species here, which if you like is kind of like, it's like a hydrated version of aluminium hydroxide. You've probably seen aluminium hydroxide written like that. So it's just like that, but you've got some water in there as well. That has got acidic and basic properties. That relates to the, if you remember the, if you look at section 2.4, period 3 oxides, if you have a look at that, you'll see there that aluminium shows amphoteric behavior there as well. And of course, it's relation to where aluminium is in the periodic table, because you know the periodic table, aluminium is right on the border. It's a metal, but it's right on the border of the non-metals. And the metals usually have basic oxides, non-metals, acidic, aluminium. You find aluminium there, don't you? Right next to the staircase line, separating the metals and non-metals. It does a few things that are a bit funny for a metal, like reacting with alkalis. And this species showing, you know, acidic behavior, when normal metal hydroxides are always basic. Okay, so in the next video we'll look at the reaction of ammonia with aluminium hydroxide and sodium carbonate also, with all of them, not just aluminium.